Okay. So for the next one, okay, here, what we're going to do is simplify it, okay? Just like before, but what we're going to do now, as you see, I'm going to show you how the factor theorem can help us here. It'll save us a little bit from factoring, so to say. Let's factor. The numerator, if we were to factor that, right, you can see here, actually, before I get to that, oh, wait, never mind. I was right. Okay. Anyway, for the numerator, right, we can see the smallest exponent of x is 2. Let's factor that. We have x squared times x cubed minus 4x squared over x squared. This is equal to x squared times this, right? When you divide into each term. So we get x squared times x, right, minus 4, like so. That's the numerator. For the denominator, same idea, right? Notice we can factor out x squared, right? Because x squared, 2 is the smallest exponent of x. And so from here, we get x squared times this divided by x squared. That's the same as dividing into each wonderful term. So from here, we get this. Okay, well, so we factored a bit. Now for the numerators, you can see, x squares, we get that x squared is a common factor, so we cancel. We're left with this. Now x minus 4, of course, you can't factor that any further. And we want to know, well, is this simplified? Well, it's really enough to see if x minus 4 is a factor of the denominator, right? Let's check that first. Because if it is a factor, well, then we're going to have to keep factoring somehow. But if it's not a factor, then we're done. Okay, so we want to know, so in other words, we want to know, is x minus 4 a factor of the denominator? Well, by the factor theorem, it's enough to see, does the denominator map 4 to 0? That is, if we replace x by 4, do we get 0? Well, in the denominator, we do. If this was not 0, then we'd be done. Okay, because that tells us then x minus 4 is not a factor of the denominator. By the factor theorem, though, this is 0, so the top and bottom do have a common factor of x minus 4. Okay. Well, what do we do next? Well, you want to factor 3x squared minus 11x minus 4. You could do that. Why don't we just divide it by x minus 4? We know x minus 4 is a factor. Oh, how do we get the other factor then? We can divide. So again, what I'm doing here is I'm going to divide this by x minus 4 to get the other factor. I mean, you could factor this thing directly, but what I'm trying to show you is you don't have to. So by dividing, right? Remember, we're doing synthetic division. X minus a number, that number goes here. Coefficients, right? We list them. 1 for each column. We bring the first number down. We have 4 times 3 is 12. 11 plus 12 is 1. 4 times 1 is 4. Negative 4 and 4 is 0. We get a remainder of 0, which is what the factor theorem told us would happen. But we also know the other factor. Like the quotient, right? 3 and 1 are the coefficients of the quotient. And the quotient is 1 degree less than the dividend. So the quotient is 3x plus 1. In other words, we have 3x squared minus 11x minus 4 is x minus 4 times 3x plus 1. So in other words, we factored it, but we used synthetic division to factor it. We knew the factor theorem that x minus 4 is a factor. So from here, plugging in, right, we plug it in, the factored form, the x minus 4's go bye-bye, and we're left with this. As you can see. All right. Are there any questions about this? Hopefully I was successful in showing you, how you can use polynomial division, or in this case synthetic division, to help you with factoring. I mean, if we did factor this, we would have to use the AC method, which involves factor grouping. I mean, it's not terrible, but I thought this would be a little bit simpler. Okay. We can also multiply, and we can divide rational expressions. We can divide them and multiply them. What's nice is it's the exact same procedures as for rational numbers. Namely, if you have two rational expressions, the way you multiply them is this. You multiply the numerators together, and you multiply the denominators together, as you can see. Okay, so that's how you multiply. You just multiply numerators together and denominators together. For the division, for division, right? Okay, so also let me say this. This is what I put here. For division, you could use this division symbol. You could also write it as what they call a complex fraction. We have the numerator is a fraction, and the denominator is a fraction, as you can see. Basically, both of these are telling you the same thing. They're telling you the same thing. You have a of x over b of x divided by c of x over d of x. And to carry out that division, you take the reciprocal of the second, right? You flip it and multiply. You take the reciprocal and then you multiply it, as you can see. We get this. So again, both of these are saying you're dividing. You take the second fraction, you take its reciprocal, so you flip it, so to say, and then multiply. Ooh. I should also say this, that b of x, d of x, and c of x we're assuming they're not 0. Because otherwise these expressions may not make sense. So, okay. All right, well, let's do some examples of this. I don't think we'll get to addition, subtraction today. I'm guessing Wednesday or Friday the latest. Anyway, let's find this product. We're going to multiply these. Multiply, right? Yeah, let me just get rid of that ink. It's not wrong to have it, but I feel better doing it like this. Okay, so we're going to multiply those together, as you can see. And when we do, we just multiply numerators and denominators together. And we're also simplifying. Okay? Now, we can see that, these are in factored form, and we can see that we have a common factor of x plus 1. So we cancel it. Doing so, we're left with this on the right side. And notice we can't simplify anymore, mostly because x minus 3 cannot be factored any further, and x squared plus 1 cannot be either. We actually saw already that if you have x squared plus positive integer, you can't factor that down any further. You can't. So we would stop here. Let me just get the recording going. Hold on, I'm not done yet.